Good. It's now preparing to live stream the webinar, so that's always a hurdle, getting onto YouTube.
Okay, I'll just sit out the way and monitor things from behind.
Okay, thanks very much.
Thanks, Dave.
I have to remember to turn down the sound. Oh, yes, sound is off on YouTube, otherwise I get echoing. Right, there we go. Well, we've got people flooding in. And Dad says, good afternoon all. Hi. Just a minute to go and we'll let people appear. We've got 44 so far. That's good. And we've probably got a few on YouTube as well. Dave Eagle is there as our technical man in black in the background. You won't see him flitting from place to place as he looks after everything. Yeah, we're live on YouTube as well, and we're recording the meeting, so that's good. I welcome everybody to this online meeting. And actually, Andrew is, of course, our president. But as you probably read on the email I just sent out this morning, unfortunately, who was to be our main speaker, Geraint Jones, has unfortunately can't do the talk because his father is seriously ill, and it's not a good time to start giving talks to the SBA. So we hope that that Geraint will be able to give his talk in the future. And because Andrew is going to give the talk, I am chairing the meeting at least until the break in the middle. So it's now 2 o'clock, gone 2, so we will carry on. So, well, Andrew, I think probably needs no introduction. Usually that is not always true, but if you've been watching TV, you can hardly fail to recognize Andrew and his famous bookcase in the background, which has appeared on numerous TV channels, Breakfast and probably quite a few others as well, giving the latest from Perseverance, because Andrew is a principal investigator on the Perseverance mission on one of the Mars cams. So he's really well placed to tell us from the horse's mouth, as it were, what's going on Mars and the very latest, and also what's coming up in the future. So thank you very much, Andrew, for standing in. And so let me hand over to Andrew. And if you'd like to start your presentation, I will fade into the background.
Excellent. Thank you very much, Robin. And let's share the screen here. Let me know if you can't see that. So there should be a false.
That's fine.
There. Excellent. Right. So I'm going to talk to you about current and future Mars missions, and I'm sure you will have noticed it's a very busy time on Mars at the moment with lots of exciting things going on, and I'll tell you a little bit about that and something about what's going to happen in the future with Mars as well. So, as I say, very exciting at the moment. So I'm from UCL's Mullard Space Science Laboratory, and the picture you see in the back there is actually a rover which is going next year. So that is the Rosalind Franklin rover, and I'll be talking about that as well because I'm principal investigator for the camera system on that. So that is the Pancam instrument that's on the top of the mast of that rover, which is going next year. And I'll talk more about that a bit later in the talk. But just to start off, really to sort of discuss a little bit about why Mars is so interesting for exploration for us at the moment. And it's because it's one of the top locations where there may be life elsewhere in the solar system beyond the Earth. And of course, at the moment, the Earth is the only place in the universe where we know there's life. But these other locations are potential places as well. So Mars is one of those. And so it's about half the size of the Earth, which meant it cooled off early in the solar system's history more quickly than the Earth did. And that meant it lost its magnetic field early on. And so it started losing its atmosphere because the solar wind can strip away at the top of the atmosphere if you don't have a magnetic field. And so Mars was a victim of that, and so Mars lost most of its atmosphere, and now has about 1% of the Earth's atmospheric pressure, and it's a carbon dioxide rich atmosphere. So that lack of magnetic field was very important in Mars losing its atmosphere. So at the top left there, that's an image of Mars, and at the bottom left, there's an image of one of Jupiter's moons, Europa. And I should say these are not to scale with each other. The scales are written on here. So Europa is about a quarter of the size of the Earth. And this is an icy satellite of Jupiter. It contains a liquid water ocean underneath that icy crust, which you can see the outside of there. It orbits relatively close to Jupiter. But it's got water underneath that crust, and it's got conditions which may mean that there's life even at Europa now. So Europa is one of the amazing targets for the future to be looking at for signs of life. And actually the European Space Agency's JUICE mission will be going to Europa as well as to Ganymede and Callisto. We'll be doing flybys of those. And in particular, it will be orbiting Ganymede. So that's the next moon out from Europa. It's the largest moon in the solar system, and it has its own little magnetic field. So it's a very interesting place to go. And that's the first time an icy satellite will have been orbited. And that also has a liquid water underneath its icy crust. So Europa, Ganymede, and Callisto, but in particular Europa, because that ocean is in contact with rock at the bottom of it. And so we think that that gives a good chance for life perhaps being on Europa now. So another potential place for life in the solar system is Enceladus. So that's at the top right there. So that's one of the moons of Saturn. So the Cassini spacecraft and the Huygens probe visited the Saturn system. Huygens landed on Titan, but Cassini did a number of flybys of Enceladus and discovered watery plumes coming out from these so-called tiger stripes in the southern hemisphere, and so that again is signs of a liquid water ocean underneath that icy crust. So Enceladus orbits relatively close to Saturn as well. So this is a bit like the Europa of the Saturn system. So it's got the right conditions, and Cassini also discovered things like hydrogen and the right chemistry going on there. So again, that is another potential location for a simple type of life now. Just below that is Titan. This is another thing which is worth mentioning when talking about potential habitats in the solar system. Titan is another moon of Saturn. It orbits further away than Enceladus does. And actually, with our instrument on the Cassini spacecraft, we discovered extremely heavy ions, which are part of a prebiotic chemistry going on with Titan there. So we were lucky enough to be involved in that amazing discovery about Titan. So Titan is another place which is worth considering for potential more like future life, because it's too cold at the moment. The surface is 93 Kelvin, so it's minus 180 or so degrees centigrade. So very, very cold, colder even than the surface of Mars on a cold night, but which is about minus 90 to minus 100 degrees. But Titan, much colder, minus 180, and so we don't think there's life there now, but there is prebiotic chemistry. It's the only moon in the solar system with a significant atmosphere. That atmosphere is made of nitrogen and methane, mainly nitrogen, but a little bit of methane in there. And there's lots of reactions in the atmosphere which form that prebiotic chemistry going on in Titan's atmosphere. So that's a very exciting place also, but probably for future life rather than current. And then Venus. So just last year, it was announced that in the clouds of Venus, phosphine was discovered. That's a possible biomarker, and I know, in the scientific community there's some doubt about whether that is signs of life or not. And the authors of the paper, Jane Greaves and colleagues from Cardiff, were the authors of that paper, and they found phosphine in the Venus atmosphere. So it at least goes onto the list as something for potentially for a place where there could perhaps be life. So we have all of these amazing destinations inside our own solar system. And then, of course, this can tell us about extrasolar planets around other stars as well. We have our own examples in our solar system where we can compare and contrast with the amazing exoplanet discoveries which are going on. But of these, Mars is the nearest, the easiest to get to, and one of the places where there could have been life when conditions were different about 3.8 to 4 billion years ago. And so our quest for life on Mars, started a long time ago, actually with the Viking missions in the 70s, but we're continuing with the missions today. We haven't found life anywhere yet on any of these objects, but we're looking for the conditions for life and then looking for life itself. And so the results which I'll tell you are relevant for that. Okay, so this just sort of compares Mars 3.8 billion years ago on the left-hand side there, looking a little bit Earth-like. And just to remind you, the solar system began about 4.6 billion years ago. And so 3.8 billion years ago is a long time ago in the solar system's history. But at that time, that's the time when certainly, Mars had a magnetic field, it had volcanism going on, it had water, possibly even water on the surface. So this simulation on the left-hand side shows you what Mars might have been like at that time, with water on the surface, water in the atmosphere in the form of water vapor, and then potentially water at the poles as well. And so very Earth-like. And that time, 3.8 billion years ago to 4 billion years ago, is the time that we know that life actually developed on Earth. So we think that there might have been an independent start of life on Mars, perhaps at the same time, because conditions were very different at that time compared to what they are now. So on the right-hand side here, we can see what Mars is like now. So it's very dry, cold and arid. In fact, it's really cold on the surface of Mars. It goes from maybe 0 to 10 to 20 degrees on the sunlit side of Mars near the equator, down to -90 at the Perseverance landing site, and down to even -100, -120 at a lot of places on Mars at night. So Mars at night is very cold. So every day and night, you get that big temperature swing from relatively warm on the day side to very cold on the night side. So the surface of Mars now is not conducive for life. It's got that very cold environment. It also, Mars has this very thin atmosphere left over from the fact that the magnetic field was lost, but we now have 1% of the Earth's atmosphere of the Earth's atmospheric pressure on Mars, and so that thin atmosphere means that the Martian surface is bathed in ultraviolet from the sun. So that really is not good for life at all. So ultraviolet radiation. There's also radiation from the galaxy and from the sun in the form of solar energetic particles. So that means that the surface of Mars now is really not conducive for life at all. And so looking underneath the surface of Mars is what we need to do to look for potential past life on Mars. Okay, so, and we can think about the requirements for life. What do we actually need for life as we know it, if you like? So we have liquid water as one of the most important things. So again, this picture of early Mars on the right there shows that there could have been liquid water, so looking very much Earth-like here as what Earth is like now. Of course, we know there isn't life now on Earth. So liquid water, very important. We need the right chemistry. So this involves for Earth-based life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's part of the ingredients for life. We need a source of heat, and we need enough time for life to develop. So those are the sort of 4 things that you need, if you like, for developing life anywhere else in the universe. And looking for life on Mars is something which we're very much trying to do with the current and future missions. So on to the current and future missions then. So there's a few current missions which are not mentioned on this slide. So that includes Opportunity, which is on the Curiosity, which is on the surface and still working. There's Odyssey in orbit, and Mars Express, the European Space Agency mission, and Mars Reconnaissance Orbiter. So all of those things are operating and sending back data. But I particularly listed these missions on the slide here. So on the left-hand side, we have the European Space Agency and Russia working together. So we have the Trace Gas Orbiter, the first mission of the ExoMars program, which was launched in 2016. It arrived into its orbit at Mars. And so that is looking for trace gases in the Martian environment, principally methane, but also looking for other trace gases as well. There have been some very interesting results published from that mission about things like the water and heavy and light water, so deuterium and hydrogen. The ratio of those is very important in planetary exploration, and also how water moves around and other trace gases as well. So that is sending back some very important information. There's Rosalind Franklin. This is our rover, which I mentioned before. So that is going in next year now. So the image of that on the right-hand side is an artist's impression. And then, of course, NASA, very busy at Mars. And so they have, as well as the missions which I mentioned, there's also InSight, which is on the surface, launched in 2018. It's on Mars. What this is doing is not looking for life. It's looking for looking at the interior structure of Mars and trying to understand that in more detail. And I think there was a talk at the SPA about that fairly recently of looking for Mars quakes. So you basically have an asteroid or something coming in, hitting the surface, and that makes vibrations in the surface. And with that, you can try and find out about the interior structure of Mars. And so InSight is specifically looking for that. And actually, there is a UK-built seismometer on that mission. So Imperial and Oxford work together on that seismometer. So that's sending back some really exciting results. There's Perseverance, of course, which landed just in February this year and is on the surface now, and I'll talk more about that in a moment. So launched in 2020, landed in February 2021. And of course, that has the Ingenuity helicopter, which I'll also talk about, doing the first flight on Mars, and we'll see more about that. Also this year, it's very busy because the UAE have a mission, the United Arab Emirates. So the HOPE orbiter arrived also in February 2021. And I'll talk about that a little bit as well. And also China has a mission. So the Tianwen-1 orbiter, there is also a rover. So both of these launched last year. The orbiter successfully made it into orbit. The rover actually is due to be landing on the surface in May this year. So you can see it's a really busy time at the moment with these missions. So Perseverance, the HOPE orbiter, and the Tianwen-1 mission, and I'll talk about all of those in a moment and give you a bit more information about them. So very exciting time. You'll also notice that every 2 years or so, there's the chance to launch to Mars. That's because of the way the planet lines up. You know, the fact that Mars's year is about twice an Earth year, so you get launch opportunities every just over 2 years to send something to Mars, and so that's why we have 2016, 2018, 2020, and 2022. Those are the launch dates. And as I say, these three have actually arrived at Mars this year. So it makes it 2021 a really exciting time at Mars. So this is rather wordy view graph. Apologies about that, but this is a little bit more information about the HOPE mission. So this is the first Arab mission to another planet. And this fits in, the science which it's doing is it's a little bit like a weather satellite, if you can imagine that. So it's looking at the lower atmosphere with the imager experiment and also with the infrared spectrometer. There is also an ultraviolet spectrometer. So it's looking at sort of holistically from the atmosphere of Mars, from the surface all the way up to its interaction with the solar wind, and so that's where it fits in the sort of global Mars exploration initiative. So it's in orbit around Mars now successfully. It's looking at things like climate and dynamics and global weather patterns, looking at weather and lower atmosphere effects on the hydrogen and oxygen escape, looking at the structure and variability of water in the upper atmosphere and the escape of that as well. So it has 3 instruments on board, which I won't go into detail of, but each of those is playing its role in, they're all imagers at different wavelengths. So we have basically a visible imager, an infrared one, and an ultraviolet one. So it's using that combination to tell us more about the atmosphere of Mars. But of course, they can take pictures as well. And this was their first image of Mars. So very good image. showing just at the middle here, this is Olympus Mons, the biggest volcano in the solar system. So you can just about see that in the middle there. Lighting conditions not perfect, but for that. But you can see these 3 volcanoes here. These are the Tharsis volcanoes, and so very good quality image, and some very good quality data from the other instruments as well. But I'll not dwell on that in great detail. But it's working very well, sending back important information, and there will be international collaborations working on the data of that. So this is a very exciting mission. Okay, so the second one is China's Tianwen-1 mission, which I mentioned. So this is the first Chinese mission to Mars. Of course, the Chinese currently have a rover on the far side of the moon from us, and that's still working well. But this is the first mission to Mars. So its objectives are to look for things like life and habitability, look at soil composition and water ice distribution, and look at the atmosphere and ionosphere. And I won't go into detail of what's on the spacecraft, but it does have a payload involving images and surface radar and this sort of thing, and also experiments to look at the solar-wind interaction. So the normal type of thing for an orbiter. But it also has a little rover as well. So this is the first time that China has tried to do this on Mars. As I mentioned, the plan is to land this next month in May. And just today, actually, its name was announced. So the name is Zhurong, which means it's to do with fire, one of the gods of fire. And so this is in ancient Chinese history. And so this is to do with igniting interplanetary exploration for the Chinese space program. So this also has a payload here, which is in detail there for those that are interested. But basically, we have an orbiter from China and also this rover. So this arrived on the 9th of February. The UAE mission arrived on the 8th of February, basically early February. And then just a little bit later in February, we had the Perseverance landing. And so Perseverance here, so this is the 5th NASA Mars rover. Its scientific objectives are to determine whether life ever existed, to characterize the climate, characterize geology, and prepare for human exploration. So this is, there's some exciting results from this at the moment. And of course, one of the things of this is to cache samples on the Martian surface for later return by a Mars Sample Return mission. That's what this MSR stands for, Mars Sample Return. And so Perseverance, once it starts its main mission after dealing with the helicopter, which of course it's famously been doing this week, it will be looking at the surface. It's landed in Jezero crater, which is a very good site for looking for potential life or potential signs of life. So it will do some onboard analysis, but it will also cache samples for later bringing back by this NASA ESA Mars Sample Return. So this is its payload. So Mast Cam Z is the zoom camera system at the top of the mast. That's the thing which has been sending videos of Perseverance as its of Ingenuity, the helicopter, as that has done its stuff earlier this week, and there's another flight of that due tomorrow, incidentally. There's also other cameras, so super cameras got a laser, so you can look at composition. There's a subsurface radar. There's something which uses spectroscopy, Raman spectroscopy, so that's by looking for fluorescence, basically. And again, you can get composition. There's an X-ray chemistry instrument and a weather station. But interestingly, there's MOXIE as well. So this converts carbon dioxide to oxygen. So just yesterday, we heard that has successfully worked in producing the first oxygen from carbon dioxide on Mars. And that's potentially something which will be useful for future exploration of Mars, potentially even eventually by humans. And so that's something which is very interesting. There's a large turret on a 2-meter robotic arm, and that's being shown in the top right image there. And of course, the little helicopter, which is the star of the show at the moment. So this thing on Earth, on Earth or Mars, its mass is 1.8 kilograms. On Mars, it weighs a third of what it would weigh on Earth because of the lower gravity. So 1.8 kilograms. So this is less than 2 bags of sugar, and on Mars even less. It has these rotor blades, which are about 1.2 meters across. They weigh about 60 grams each. And because of that thin atmosphere, these have to rotate extremely quickly in this thin carbon dioxide rich atmosphere. So they rotate actually at about 2,400 revolutions per minute. So if you think about that, that's 40 revolutions per second. This thing is going around really fast. And of course, it's shaped to get the lift which you need in this very thin atmosphere. So it has to displace enough mass of air to get the thing off the ground. And so it successfully did that. So it will have up to 5 test flights. We've already had 2. So the second one we just heard about yesterday, and then the next one of these is tomorrow. It basically has another just over a week left to do its investigations with the helicopter before the rover takes off and looks for signs of life. So it's landed in Jezero crater near an ancient river delta. So again, a wonderful place to be looking for potential signs of life on Mars. So just some of the data from this, and I can't resist showing some of the amazing images from our Mastcam-Z instrument. So Jim Bell at Arizona State University is the principal investigator of this, but we're co-investigator, so involved. And I have a student working on looking at seeing water in the Martian atmosphere, hopefully from the cameras. And so she is putting together some ideas for that, and at the moment, of course, it's taking its first images. So this was the first panorama which was taken from the from Perseverance at the landing site with Mastcam-Z. So this is the scientific camera system, very good resolution. You know, you can zoom into this and not lose very much, and some amazing imagery already available. And we have filters with that, and so we'll be able to do geology and as well as the atmospheric science, which we're particularly working on. But that will be a very exciting, already is a very exciting mission. And the videos and images as Perseverance landed, those again are a first in space history of actually seeing the landing going on, you know, from a very adjacent camera system. So incredible. Okay, so this was how that first panorama was put together. So from a number of different images. So the red on top of this image here, this shows the individual image frames. So each image in this case is a 2 megapixel, it's a 2 megapixel camera. And so these are stitched together to produce the image which you saw on the previous slide. And so this was how that was done. And amazingly, this was programmed before the landing, you know, so it wasn't known exactly how the thing would land, or, you know, I mean, it's a large lander, so and the wheels had to be on the surface the way the sky crane worked in the landing. So it had to be about right, but it was amazing for the team to see this come down successfully because this was all pre-programmed before the landing. So also some images here. So one on the left-hand side showing some of the hardware on the spacecraft. On the right here, this is one of the nearby bits of the river delta. So the team are considering at the moment exactly which way to go and to plan the drive. So once the helicopter business is finished, to start to investigate these areas, looking for potential habitability. So this, it has a drill on board, so it can drill up to 6 centimeters. It can core rocks effectively up to 6 centimeters. So that's getting below the really sort of harsh environment at the very surface. But it's not drilling as deep as we are with ExoMars. And so that I'll talk about that though in a moment. But it will be able to get these samples and cache them on the surface for bringing back by the later mission. And on the bottom here, this is again one of the amazing panoramas showing the beginnings of that river delta region. Okay, so this is the first movie of. And this is not a CGI, you know, this is actually a real movie of the helicopter as it sort of prepared to take off just a few days ago. So I'll just run the video, and of course it starts off on the surface for a start, and as the video develops, here's the rotor blade starting to move, and this is sampled. Not every thing is found, and so it successfully takes off the ground. The first time this has been done, a powered controlled flight, turns around a little bit. This was what was pre-programmed before the flight, so you can see to some extent the blade rotating there during the flight. Everything worked very well, very nominally, and then of course the landing back on the surface again. So amazing to see that actually work. And of course, this is being developed, or this was developed as an engineering test, and so that's NASA's logo, reminding us that it's them that did it. So absolutely fair enough. So this is an incredible video of the first flight, and of course the video of the second flight is available now, and it all is working very well. So this is a technology test. I'll just run the video again just while I'm talking about this. So this is a technology test for future exploration missions. Just an additional thing to have as a possibility for exploration. So it's not doing any science with this particular mission. It does have 2 little cameras on board, which we've seen some of the images from, but this particular image sequence is taken from Mastcam Z on the rover. So that has the amazing video capability which allows this to be done. And so the Mastcam Z team, as I say, led by Jim Bell, but Maylin are involved in this, and they've done an amazing job of putting together the command sequences which you need to do that type of video, as well as taking the images and getting the frames right. We've also seen some zoomed in videos as well, and so amazing success. Okay, so but as I say, it's mainly an engineering test for future missions, and so that will be something which can be used in the future. Okay, so onto the next slide, hopefully. Okay, right, so this goes into a bit more detail about Mars sample return. So Perseverance, which is there at the moment, and this is an ESA image, and I should say that the Mars sample return is going to be joint between NASA and the European Space Agency. So you'll see it's a complicated mission sequence. So actually the first one is this Mars 2020 mission, so it's Perseverance, now successfully on the surface. So that's that NASA rover. So that will be caching samples. So the red bits which you see are the samples which are cached. It has 38 tubes on board, which it will put samples in for later bringing back by these future missions. And so the second launch here, which we hope is going to be 2026, but we'll see once this becomes an approved mission. So what this will do is deploy a sample fetch rover, and this will be a European Space Agency rover, and in fact Airbus and Stevenage have been selected to build this rover, and so it's a very exciting thing for the UK and for the European Space Agency, this mission. So that will collect the samples eventually to be brought back, and so then we have an ascender to an orbiter, which is in orbit around Mars here, and then this is eventually brought back to Earth. And so we think probably about 2032 to 2034 will be the date when we can get the samples from Perseverance back to Earth. So very exciting. So in the meantime, as well as these missions going off in 2026 and 2028, we have our own mission. So this is taking off next year. So this is the ExoMars Rosalind Franklin rover. So this is the payload. This is what's on that. So just to remind you, this is a rover, which is a 300 kilogram rover, so smaller than the Perseverance rover. And this will land on Mars. So this is its payload. So on the left-hand side, these are the instruments which give us context on the surface. So there's Pancam, which is our camera system, and I'll talk more about that in a moment. There's an infrared spectrometer, which helps with determining the minerals, adding to our visible data with Pancam. There's Wisdom, which is a subsurface sounding radar, so that will be looking for outcrops and for ice underneath the surface. There's Hadron, which is a neutron detector. So that looks at how cosmic rays interact with the water just underneath the surface, and it detects a particular energy of neutrons to do with that water underneath the surface. There is also a close-up imager. So that's a bit like a geologist's hand lens, sort of peering at a rock. So that is complementary with our Pancam and our high-resolution camera, where we can do that to some extent as well. So there's also a little visible and infrared detection system in the drill itself. So this is the drill, and inside that we have this instrument called MARMIS. So that will get the geology from where we're drilling underneath the surface. So with this, we're drilling up to 2 meters underneath the surface, so much further than we can drill with Perseverance or indeed Curiosity. So actually this will go 2 meters underneath the surface, and that gets below where the radiation can be a problem. And so this is the unique thing about this particular mission. So once it has got the sample from up to 2 meters underneath the surface, it looks at it with these instruments. So there's micrometer, which is a visible and infrared spectrometer. There's a Raman spectrometer, so again looking at fluorescence to get composition of the rocks, and then a Mars Organics mass analyzer, so that we can analyze organics, so carbon, carbonates, things like that, all the way up to amino acids. That's the type of things which we're looking for, the building blocks of life. We can look at chirality with that. So this is left-handed and right-handed molecules. So you may be aware on Earth we use left-handed and right-handed amino acids and sugars for life, and so that's the type of thing which we are able to do with the Rosalind Franklin rover. So very exciting. And you can see the UK flag here is on the left-hand side of the top of Pancam, because we're the principal investigator group at MSSL for the Pancam instrument, and I'm the PI for that. We have a big team in the UK and elsewhere working with us on that, and so it's a delight to work with them. Also, there is involvement in the UK in Leicester University in the Raman spectrometer. So they and Rutherford Appleton Lab Space are involved in that, but Leicester are the academic part of that. And then industrial, actually, the UK is very well positioned in this as well, because the UK has built the rover. The ExoMars Rover was built in Stevenage. So that's one of the things that gives them heritage for being able to do the sample fetch rover for the Mars sample return mission. So altogether, both academia and industry playing very important roles in the Rosalind Franklin rover mission and in the future missions. So the rover itself, so we're looking for life on Mars. Our launch is 21st of September next year. We land on the 10th of June 2023, so that's the date for the diary. We drill up to 2 meters underneath the surface, and we have both context and analytical instruments. So I'll just run this little movie. This shows the rover, the drill at the front here. Here's Pancam at the top of the mast, the infrared spectrometer just below that. Here's the solar panels. These are the wisdom antennas for looking underneath the surface and putting that data together with what we get from the images. And this shows a sample being taken from underneath the surface and put into this analytical drawer, which then gets pulled into the rover. And the analysis is done inside the rover, and we send the data back to Earth. So with this one, we're not bringing samples back to Earth. We're doing the analysis where we are in situ. At our landing site, which is like Jezero Crater, is another really good place for looking for signs of past habitability and even life. So very exciting mission. And this was taken before the days of social distancing, just to show you the size of the rover. So this is some of our Pancam team during one of the meetings at ESTEC in December 2019. So before we got to social distancing, of course. And this is just to give you an idea of the size. So Pancam actually sits 2 meters above the surface of Mars. And these are just a sort of few passers-by from the Pancam team. Okay, so why is the rover called Rosalind Franklin? So this is after this brilliant X-ray crystallographer, Rosalind Franklin, who took this image, photo 51, of a fiber of DNA. And this was critical to Watson and Crick's discovery of the double helix. She also did important work on the structure of carbon and viruses. So very important work being done there. And this was the famous photo. So I can't wait to see what our 51st image on Mars is going to give. So we'll see what happens. But this is a very appropriate name for the rover. So the UK Space Agency, who are our main funders, by the way, and I should say thank you to the UK Space Agency for the funding, had a competition to name the rover, and the most popular and the most appropriate really was Rosalind Franklin. They had 36,000 entries into that competition, so there's a lot of public interest in what to call it. There were the usual things like Rover McRoverface and things like that, but this is a much better name because Rosalind Franklin deserves the recognition for this. In fact, she missed out on the Nobel Prize, unfortunately, for the double helix, but nevertheless played a very important role in that discovery. So it's very appropriate that we're calling our rover after her. So just a few things here about why do we need to drill. So I mentioned the surface of Mars is really harsh for life. It's very cold. It's bathed in ultraviolet. It's bathed in radiation from the galaxy and from the sun. So we have to drill deep in order to do that. So we need to get below 1 millimeter to get below the ultraviolet. We need to get below about 1 meter to get underneath where oxidants can be a problem. And we need to drill actually 1.5 meters underneath the surface at least to have the chance really of seeing past life. And so this is the important thing. And actually, I had another PhD student a few years ago working on this, and he actually worked out that yes, 1.5 meters was and below is where you really need to drill to be able to get signs of past life. So that's why we're drilling that deep. So exciting times, and we have a good chance perhaps of seeing biomarkers, as of course do Perseverance with their amazing mission on the surface at the moment. And so they're looking for similar things, but not drilling quite as deep. But overall, these are very complementary missions, and we're working together really. Okay, so that's the idea, to get samples. So where are we going to land? So we're going to land at the so-called Oxia Planum. So this is part of Mars. It's near the equator of Mars, in between the northern hemisphere, which is relatively low areas on Mars. I should say the image on the left is a globe of Mars, and the colors are from the Mars Orbiter laser altimeter. So those give you the height of different features on the surface. So it's very low is the blue stuff here, going to extremely high is the red, and so this is in between the two, and this is where an ocean might have lapped on a shore for some time. And there is definitely evidence from orbit of things like clays in this area, phyllosilicates as they're called, and these are signs of past water at this site. So it's a really good site to be exploring. And so in detail, where we're going to land, these are the 2022 launch ellipses where we could potentially land. And so we this changes a little bit during the time of the launch window. We have about a 2-week launch window to get the thing off, and we get the slightly different landing ellipse with those different opportunities, and those are shown on here. But this is it's a very old region, even older than Jezero Crater, where Perseverance is, just a very slightly older. So again, this gives us a really good chance. 3.9 billion years old, these clay-bearing rocks are, and it's the remnants of a fan or river delta, perhaps near the outlet of Kogoon Valley, so this particular large region. So very exciting mission, and I'm so privileged to be leading the camera system on this. So this is the science eyes of the Rosalind Franklin rover, and so we have a number of different elements. This is a CAD model showing the innards of this, and so we have 2 wide-angle cameras. So these behave a little bit like eyes. And then we have a high resolution camera as well, which is another eye, which sort of with a telescope. So we're able to look very closely at rocks in high resolution. We have a there's interface electronics here. The whole thing is housed in an optical bench, which sits at the top of the mast here. There are also the so-called small items. So we have a calibrating target to get the colors right. We get stereo with the 2 wide-angle cameras, 50 centimeters apart. We get shapes and scales from the fiducial markers and from the Pancam calibration target. And actually, I've got a model of Pancam itself here. So this is not the real one. The real one's on the rover, but this is a model of Pancam showing the wide-angle cameras here at the end, so more widely spaced than the human eyes, then the high-resolution camera here, and so that's what one looks like, and that's a life-size model made in metal by our amazing engineering colleagues at the lab. Okay, so we have, that's the components of our camera system, and these are the people that built it. So on the right-hand side, this is some of the engineering team, including our project manager, Mary Carter, here. This is with the camera in the back of the car as it's about to go around the M25 and deliver to Stevenage. So some of the other engineering colleagues who were really responsible for the delivery of this, of Pancam on time in 2019. So Barry Whiteside and Craig Theobald and Tom Hunt and others involved with this. So, and this is sort of the who did what. So ourselves, we did the filter wheels. The wide-angle cameras came from Switzerland, from Thales Alenia in Switzerland. The high-resolution camera from our colleagues in Germany, so DLR and OHB, their industrial partners working together. We did the electronics and the optical bench, and then Aberystwyth University did the small items. But all in all, we have a science team which has 9 nations on it, so a very international science team. And this is one of our recent meetings. Again, you know, before we had lockdowns and things like this, so we didn't have social distancing at this time, just to give you an idea of some of the people involved and the sort of diverse team, actually, which we have working on Pancam. Okay, so this is the filters which will actually be looking at Mars, and so there's 11 of these filters on each of the wide-angle cameras. So we're basically with these separating the colors of light out so that we can look at geology and we can look at the atmosphere. So geology, we're looking in particular at water-rich minerals. With the atmosphere, we're looking at water vapor, and the colors, these are the wavelengths and the widths of those filters, and these are the actual ones which will be looking at the Martian surface. So I can't say how excited I am to be able to show you a picture of the actual filters which will be looking at Mars. So just amazing. We also have a color high resolution camera, so that provides the texture of the rocks and some of the details within the rocks. Okay, and these are some of the blow-ups and other views of the camera system. So here you can see the filter wheel. So my colleague did an engineering rendering of this using our CAD information, of course, of the actual experiment. So with here you can see the filters. And then our Aberystwyth colleagues did a rendering of what Pancam looks like on the surface of Mars. And so again, this is a rendering, not a real thing, but it gives you some of the real dimensions of the rover parts and the instrument as well, with a Mars mock-up behind. So we've used this a lot in the field. So there's an emulator which we've used. So Aberystwyth built an emulator. We also built one at UCL, which one of my other students has been doing for 3D analysis. So Eleni, she's recently put in her PhD thesis to be examined soon. But this is the Aberystwyth emulator, which has been taken into the field to places like Iceland, to Svalbard, to the Atacama Desert in Chile, lots of different field tests. And here's some of the 3D data. So you can we have the software to be able to show things in 3D. And that also has, for geologists, what they call dip and strike. So this is the layering, looking at the layering of the rocks, the sediments of the rocks, and trying to link up and see what links with what. And then on the right-hand side, we can do things with composition. So this is another UCL PhD student who did her thesis in 2015 based on some Iceland field trials, and so she was able to use the colors of the filters to separate out the different minerals, and that's shown on this illustration here. This gives you an idea of the type of thing you can do once you stitch those individual images together. So very exciting. This was taken in the Utah desert in 2016. You can tell it's on Earth because the sky is blue. There was also a truck, which you can't see just over to the right-hand side here, but so we know it's on Earth. But with the real thing, once it gets to Mars, is going to be spectacular imagery, and so we can see very nice imagery, just like we're getting from Perseverance at the moment. Okay, another trial in the Atacama Desert, which showed some very interesting spectra of particular areas. You can see that the Atacama is one of the driest places on Earth, and so one of the really good places to do field trials. So with this, we had a rover in the Atacama Desert, a trial rover, and then we had an operations center back at Harwell looking at the analysis of this. So of course I was at Harwell, unfortunately, rather than the Atacama Desert, but anyway, and again, this is pre-lockdown, but we've done lots of testing to make sure both the hardware is doing the right thing and also the team is prepared for the operations on Mars. As I said, it's a really big team effort, this. And that's just the geology image again. So I'll just show this very quick video which shows you our landing sequence. So all going well, this is what will happen. So that's approaching Mars. That's the capsule being released from the orbiter, from the carrying system. It has heat tiles on the front to stop it burning up. And parachutes deploy. We've had some trouble with the parachutes, which meant we couldn't launch this year. Last year, sorry, and so with COVID as well, that was too much. We had to delay the launch to 2022. Anyway, so then we have the deployment down towards the surface. Retro rockets slow it down on this Russian-built landing module called Kazachok, and then the rover is on the top there. So unlike Perseverance with the sky crane, we have this landing system to land successfully on the surface. So we do the first few measurements. With the solar panels, we get power. Oops. That's skipped, unfortunately, to the end. But I think that's probably enough of that movie anyway, because we're running out of time. Okay, so this is some of the integration going on at our lab, and so this is one of our technical staff actually putting things into Pancam. You can see the filter wheel here. All this done under very very planetary protection conditions, they're called. So we have to make sure that we're not taking life to Mars to measure that. So we have to be, these are kept extremely clean in very low class, very high class clean rooms, but with low numbers of spores that we actually have to count the spores which are accumulating, and so using monitoring. And so we did all that, and of course we know much more about that now because of COVID things. But anyway, this is what we did with the hardware pre-delivery. This is what Pancam looks like inside. So this is the actual wide-angle cameras, the little filter wheels on front here. These are 50 centimeters apart, so we get better stereo than the human eyes can do. The high-resolution camera, the light comes in here. There's a mirror here, a focusing mechanism, and then this is the image plane here. And so this behaves a little bit like a telescope, and so we can get very good close-ups of rocks. Okay, so these are the filters, and so astronomers, of course, know all about filters and splitting light up. So that's what we do, and so these are the filters which were actually. This is before delivery, after delivery, but before putting them into the filter wheels, and so you can see the different colors here. And so there was ESA did a press release about this because these look a little bit like contact lens cases, and you get the idea of these are what we put in front of Pancam's eyes to split up the light so we can do the geology and the atmospheric science. Okay, so this is Pancam on the rover, so all of this is flight hardware. So this is the rover undergoing some tests last year in Toulouse. These were the so-called thermal vacuum tests to make sure that that things would work. So this is Pancam, the flight one on the top of the mast. This is a picture of the flight Pancam in our clean room. These are the small items, so-called, again in our clean room. We had to do the final processing of that, having been made by Aberystwyth University, but with the fiducial markers here for the shape, the calibration target for colors, and the rover inspection mirror, so we can see underneath the rover. So, and again, I'm so proud to be able to show this. It's the actual flight rover and flight hardware. The flight rover is now back in Turin doing some more tests before. I think it's next April, so about a year's time, when it goes out to Kazakhstan, to Baikonur, the launch site for the launch. And so there's more tests which need to be done before that. So this was the installation of our camera system, which was done in August 2019. And so this is my colleague Matt Gunn from Aberystwyth University inspecting Pancam to make sure it looks right on the top of the mast. And we also did a test, a sort of end-to-end test with that. These are the Wisdom antennas here, and showing Pancam going on there in August 2019. And this is Matt actually holding up a piece of paper here, which has on it, it says "Hello Mars." And so this is our first light image on the rover in 2019. Going all the way through the rover systems, everything worked fine. So it says "Hello Mars." And so this, of course, we can put together red and green and blue to get color, which we will be doing for Mars, but this was just our first image. So again, it's very proud to be able to show that. Okay, so our actual mission, so the launch is 20th of September and in CEST, that's the launch date, and then the landing on the 10th of June 2023. We know the time. It's basically Isaac Newton in the driving seat for most of this, and so there might be the odd in course correction during the flight, but this is the idea, getting to Mars. And so very exciting time that will be to see this actually going to Mars. So I've got here a very quick, I know the time's running out, but I'll show this very quickly, which shows some of the engineering team as well, which have been involved in this.
Pancam is a panoramic camera. Yeah, that's what it stands for.
Pancam, this is the scientific eyes of the Rosalind Franklin rover. So we're looking at the scene on Mars, trying to do some geology, trying to do some atmospheric science.
The instrument is a fairly plain white box, essentially, but it's what's inside the box that's interesting.
We've packed as much science as we possibly can into what is basically a camera system.
We have two wide field cameras on the ends.
Stereo imaging cameras of the wax, one at each end. So on a stereo baseline of about 500 millimeters for stereo imaging and plotting of routes on the Martian surface. So looking at what's in front of the rover and working out where it can go.
So each of these wide-angle cameras has a filter wheel in front of it with 11 positions, and we can move that around to look at the different colours of the light coming from the surface of Mars. And so with that, we're able to not only build up a colour picture, but also to look at composition of the rocks, in particular looking at the light which is reflected from the rocks, to look at the minerals in them, and to look particularly for water-rich minerals, because of course we're looking for water and life on Mars.
And then we have a high-resolution camera.
So the HRC light path comes in, goes, hits a fold mirror, goes through a focusing mechanism in this area, and then projects onto a sensor down at this end.
This will enable us to actually see fine-scale, small-scale details on the Martian surface. For example, texture on rocks, or it will enable us to see single grains on the soil, and that's very important for the geological investigation of the surface.
We were PIs on the optical bench, and we produced the PIU and DC-DC converter, and they were built here.
We already delivered the hardware, so it is now in still finish in Airbus. Now they're putting all the things on the rover. The project starts since 2004. So we're talking about this 15 years of our life is working on it.
I remember the first time I saw part of Pancam and then got to handle some of it. And it was a pretty amazing experience to think that, things that you've touched and helped with will hopefully be on Mars soon.
It would be a fantastic discovery to actually be able to find evidence for life anywhere else on the universe, and Mars is the nearest place we can look, and so our rover mission is specifically designed to do that. Okay, so that gives you an idea of some of the team involved as well. As I say, it's a large team, and it's a privilege to be working with them. Okay, so just to finish off, so our Rosalind Franklin mission will provide an important new dimension on Mars, drilling underneath the surface up to 2 meters. that is complementary with what's being done currently with Perseverance and the other missions. But very exciting. It has its own niche, and Pancam with the other context instruments provides the geological and atmospheric context. And as I say, it's an extremely interesting and exciting time on Mars at the moment, with Perseverance on the surface, Ingenuity about to try its third test flight tomorrow. So very exciting, and of course the Chinese mission due to land soon. The UAE mission. So hopefully I've given a bit of a flavour of what is going on Mars this year. So I'll stop there. Thank you very much.
Thank you very much indeed. I just had to unmute myself and the button disappeared. There we go. Right, I'm back again. Thank you very much, Andrew. And we've got a few questions in hand, and I'm going to get in there first because you mentioned color balance when you were talking about the cameras, and NASA, when they show the pictures from Mars, often show them, some look red and some look like more Earth color. Can you explain the difference in the two appearances?
Well, the sort of you can tune what you do with the colours. You can do that as they would appear on Earth in sort of terrestrial lighting. I mean, you have the calibration target to get the true colour. What we're really interested in is the true colour coming off, and so to get the ratio in particular between different wavelengths, and so that's what we do with the calibration target, to sort of tune the colour balance of the images. But overall, yes, we're able to do that with the color calibration target.
Okay, so which is the correct color when we look at these pictures? Is it the orange color or the blue color?
Well, they will always say which is the true color. So yes, orangey or bluey. I think it depends how you can stretch the color table and sort of adjust the colors which you see to be a little bit like how you would see it with Earth illumination or how you see it with the Martian illumination, and so it's the true color ones which are the ones which are the actual colors. And the other thing about doing the correction is that you can get dust on the calibration targets as well. Of course, that builds up during the mission, so you have to be careful to correct for that in the right way as well. But Mars is basically reddish. Yes, the real color really is actually reddish.
Okay, because when the sunlight is coming in through the atmosphere on Mars, it is slightly non-white. It's not the same color as it would be on Earth. Is that the case?
The scattering is different, yes, because the atmospheric density is less, and so the amount of scattering you get is just very slightly different, and so that gives you different tinge. But you can take that into account in the processing. Yeah.
Okay, questions from online. Daz wants to know, got a couple of questions here. I'll put them both to you. Do you know what speed the rotor blades reached before lift was achieved? And the second question is to do with the ESA rover. How many drill samples will be done on the ESA rover?
Yeah, so the drill speed, I mean, the maximum speed is 2,400, and I think that's what they ran it at to be able to do that, the test flight so far. Also, they transmitted a lot of engineering data back to be able to look at that to see what was needed, because there are a lot of automatic systems on board. It's got quite a lot of computing power available to actually do that. So it uses the images as it flies, and it uses the performance to be able to do the flying. So the exact rotor speed would be part of that telemetry. So 2,400 is the nominal value, so of the maximum, but there will be somewhere the records of exactly what was needed. So it will be interesting for the team to look back at that. I'm sure they have already. So as regards how many samples we can get with ExoMars, so we can drill in several different places. There's, I think, 6 different vertical surveys, 2 complete vertical surveys down to 2 meters, and then 6 times where we can drill a little bit less than that. The drill is taken in bits, so we have basically 50 centimeter components of the drill, so you need 4 of those for the 2 meters. So you can drill a little bit less, but the full vertical survey is going to be done twice. the number of samples you can actually analyze is limited. So both of those, of course, are tracked very carefully during the mission. So we have a careful mission plan, which, but part of the thing is we have to decide exactly where to drill. So that's why we need the context instruments, because you can only actually do the analysis a few times. So it's a good question, yeah.
And there's one on YouTube from Karen Martin. How has the RFR drill been designed to overcome the difficulties that InSight has experienced in drilling to the Martian surface? And I'm not quite sure what those difficulties are.
Okay, well, yes, InSight had a what's called a mole on board. So that was a mole. It had an electromechanical system inside the actual mole itself. So it was trying to hammer itself into the surface. But the difficulty it had was it didn't go down very far, so there's a rock in the way. So with ExoMars, we can look underneath the surface with the subsurface sounding radar and with the Adron, so we can see the context underneath the surface, so to see where a good place is to actually drill. But yeah, the actual thing is not an impact related thing. It's a rotary drill, a little bit like we use, but much slower than we use in domestic situations. And of course, we have a spare as well, just in case a drill bit breaks. So those of us that have done drilling at home, you get that occasionally. But yeah.
Yes, very wise practical experience there. Is there a reason, asks John Morrill, why there wasn't a spectrometer included in the Rosalind Franklin rover?
Spectrometer, well, I mean, there are, what we did was to select, or the payload was selected. I didn't select it because we're one of the proposers, of course, but we selected the instruments, at the time, which would do the best job, and so in Pancam, for example, we do multispectral work, but we use the different filters. It's actually difficult, and we did do a follow-up technological study to try to see if you could do a hyperspectral measurement with a hyperspectral type of instrument, but actually the temperature on Mars precludes that. So you have to do something like a filter wheel or a biofilter, something like that, to get the color. But the best scientific way to do it is with filters. And so because we know exactly what the filter transmission is, so we can take account of all of that in the data processing. So that's the best way of doing it. But of course, I mean, the others, the Mars Organics Mass Analyzer, for example, that does include a spectrometer for looking at the different ions, neutralizing, what you do is heat up the samples to a high temperature so that it gets to atomic and molecular state, then ionize them, then use a spectrometer to see what they're made of. And so there's a spectrometer in that. So there are spectrometers, but for Pancam, we decided not to use, we decided to use filters instead. And indeed, that's the way that Marscam Z does the same thing on Mars as well at the moment.
Okay, thank you. Catherine Grimes has got a question. Seasonal variations of methane and oxygen have been discovered on Mars. If the drill releases gas from the Martian surface, could Rosalind Franklin detect it?
Yes, so we can look at with the Mars Organics Mass Analyzer at the atmosphere as well. So we have there's a blank sample, and then we can do atmospheric samples as well. So that is another thing we can do as well as the drilling. So we can detect things like methane and other things coming from the atmosphere. So we would be able to do that. But interestingly, the Trace Gas Orbiter has tried to detect methane and hasn't yet actually detected it. But of course, Curiosity did find methane in some of its atmospheric samples. We can do the same thing, and actually we can do it slightly better with Rosalind Franklin than they can do it with Sam on Curiosity. So watch this space. We will actually be able to do that. Yes, absolutely. Yeah.
That's good. Yes, because the methane on Mars is a really big open question, isn't it?
It is, yes. I didn't go into that, but the yes, I mean, the Mars Express, European Space Agency's Mars Express discovered methane there back in 2004, and then That has subsequently been looked at with Curiosity. So Curiosity sees this seasonal variation of the methane, as was rightly mentioned, and indeed oxygen. So you can see those going sort of very close to the surface. But actually the trace gas orbiter is having difficulty finding the methane. So we're trying to understand the process, or the science community are trying to understand the process for that. So there must be some process which is keeping that near to the surface, where it's come out of the surface, to be seen by Curiosity, but then it gets high enough to be able to be seen by Mars Express. But for some reason, Trace Gas Orbiter doesn't seem to be sensitive to these low altitude things, which is surprising. But so I think that the jury is still out in the scientific community on why that is exactly. So so again, something of an area of active research.
Plenty of Mars mysteries still to come, right? And of course, inevitably it's going to put you on the spot, and I'm pretty sure you won't know the answer definitively, but what is your guess on whether there is something there to be discovered in terms of life?
The conditions were right 3.8 to 4 billion years ago for life to have developed there. So yes, from my point of view, there's no reason why we shouldn't detect it, and there's every possibility. But of course, as scientists, we're looking for proof and evidence, and that's exactly what why we're trying to send the missions there to understand, you know, first of all, the habitability, as well as all these other objects in the solar system as well. But you know, to actually do the thing of, was there life? But yeah, my hunch is that indeed life did start on Mars 3.8 billion years ago. It's probably died out now. But if there were extant life, we would be able to find that with Rosalind Franklin as well. But I think the likelihood is that it would have died out.
And just a general question about the whole idea of looking for life on Mars, and indeed such explorations as we do go for. And I'm sure it's the sort of thing that people might ask you, and people will say, well, with all the problems we've got and COVID and so on, is it the right time to be looking at Mars? What about the waste of money, all that sort of thing? What do you say to such people?
Well, yes, it is very expensive to do space exploration, but other things on Earth are even more expensive that we wouldn't necessarily want to do. But yes, there's a lot to find out about our own Earth. It was Earth Day just yesterday, I think. So, you know, our own planet and understanding it. But I mean, what we're doing is trying to find more about the different planets in the solar system to try and put the Earth into context, and that eventually ends up actually helping us on Earth as well. You know, understanding, for example, Venus started off as Earth's twin and ended up very differently, and of course carbon dioxide and global warming is a very important part of that. So understanding and putting the Earth in context is what we need to do. Understanding humankind's place in the universe, that's why we do it, and the type of thing. We can also push technology which can then be used on Earth. I mean, that's not the reason we're doing it, but we can develop technology which is useful in the medical field, for example. So there are definitely examples of mass spectrometers developed for landers, which have ended up being used in the medical field as well. So the stuff we're doing is useful in that sense. But what we're doing really is exploring and trying to understand our place in the universe. And indeed, it's not the cheapest way of doing research, but you know, we feel that the types of questions we can answer are important enough that we need to do it.
I've always been impressed by the excitement shown on the sort of programs that you might be appearing on, Breakfast and so on, when the presenters are talking about, say, the helicopter, and there has been a lot of excitement about that. And it was, yeah, from a PR point of view, it was absolutely a brilliant idea to put a helicopter there, but of course it has got a lot of potential in the future. And yeah, I've been encouraged by the sheer fascination. And in terms of fascination value alone, something like that, I compared with a lot of the things that we spend money on, super leagues and so on, you could put several people on Mars for the same price that we spend on some of these other perhaps less important things. But they all keep people entertained. That's the thing. Just as some people are entertained by football, some people are entertained by putting things on Mars and finding out more about Mars. So it's what people find interesting, and a lot of those people, I think, who say what a waste of money are just not interested in the sort of things that we're talking about anyway, and that they have very limited horizons, I always feel. Colin Pryor's actually got a comment. So it just says, so we might be descendants of Martians. And I think this is to do with stuff coming off Mars and back to Earth, isn't it?
Yes, so the sort of panspermia idea of bringing, yes, if life had developed on Mars and maybe one of the meteorites, you know, because of course during the late heavy bombardment of in the solar system about 4 billion years ago, there might have been bits of Mars driven off Mars which might have come to Earth. But yes, I mean, it's a theory, but yes, I mean, we don't know for sure exactly how and why life developed on the Earth. So again, there's research there which is trying to understand that too. And one of the possibilities may be that stuff came from other places, and certainly comets bringing some of the important, you know, which we would have heard about today. Sadly, Geraint was not able to do it, but we'll get him back. But comets bringing material to Earth and asteroids bringing material to Earth probably played a big role in Earth's history. And similarly, you know, bits from Mars, the chances are less, but nevertheless, it's a possibility. But what we really think is probably the likelihood of independent life being starting. And so that's the type of thing which we're looking for. Yeah.
Super. Well, thanks very much to you and for all the questions we've received. Now we're going to take a break from the meeting, and we'll still be here, so don't go away. This gives you 10 minutes, and I know it's now just coming up to 3:15, so at 3:25, or maybe a minute or two before, we will be resuming. And I've got an astronomical equivalent of the potter's wheel to put on video, so that there's something happening on the screen while we're away. So we will close our videos now, and I will put on the potter's wheel, and we'll see everybody back in 10 minutes. I'll be talking about what's up in the sky in the next 3 months, and then we've got Martin Ratcliffe joining us from the States to talk about the things he's been up to in the States, and also a very amusing, entertaining trip he took to the Boyden Observatory in South Africa, where he was able to observe with a historic instrument, and some of his experiments and adventures in planetary imaging. So we'll see you all in quarter of an hour. In 10 minutes. 10 minutes, that's it. Okay. Thanks.
25 past, yeah.
Yeah.
Okay, so just 3:25, so good. We can start the meeting again. So I'll be chairing this part of it, and so the first talk is going to be from Robin about what's coming up in the sky, the night sky, for the next 3 months. Over to you, Robin.
Hi, right. Let me get I realised the trouble with leaving that moon video on is that I didn't have my presentation queued up. Now I've got it lined up now, and so I've got to share my screen again. Share screen. It's amazing how these things don't appear when they're supposed to. Let's see.
Yeah, we can see it, but not full screen yet.
No, I'm trying to get it full screen now. Does that work?
Yes, that's good. Yeah,
that's good. Okay, right. Thank you very much. Pardon me. Next thing is, will the slides change? Yes, they will. Right, good. We're in business. Now, one of the things I normally talk about on these WhatsApp is what's happening with the planets. But the news is that there is absolutely no news regarding planets, because apart from Mars, which is now very distant indeed, there are just no planets to be seen. And Mars is really on its way out as far as our observing is concerned. Martin Lewis is probably trying to observe it still. He's hoping to keep going until June, but it's quite an effort because Mars is now down to just a few arc seconds across. I think it's about 5 arc seconds across, and a tiny thing, the sort of thing that in the past nobody would have ever tried to observe as a visual exercise because it was just so small. You just see a tiny little dancing blob. But with modern techniques, it's amazing how we managed to draw the information out. So instead, we're back to observing the sky itself, the deep sky objects. So this is the sky as it will appear in a few days' time when the moon's out of the way. And this is probably about 10:30 or 11 at night when it's got properly dark. Of course, this time of year, it takes quite a while to get dark. And I've drawn in just a few of the best known constellations there. Leo is the one that probably everybody knows. If you're wondering where the Great Bear is, the plough, it will be right at the top of this view, and it doesn't quite appear, but that's where the well-known plough is. But coming down, you've got Leo over in the southwest at the moment, and you recognize the lion shape of the stars there. And then you've got the bright star Arcturus, and between the two lower down mid-sky is the bright star Spica in the constellation of Virgo, and that, as you can see, there is a sort of Y shape. And below that, we've got that little quadrilateral, which is only fairly faint stars, but that's Corvus. Now, in that sort of bowl of the Y of Virgo there, this, if you look on the star map, is absolutely jam full of galaxies. But you might imagine that if you're looking with your small telescope or even a large telescope, you would just come across one after another. And in the next slide, we can see what happens if you use something like Stellarium, which is a very popular a bit of software for looking at the sky. Let me just go back and point out where we are. I can't see it too well on my version of the screen, but just about there, about here, there is a star called 6 Comet, and about here, there is another star. As I say, it's the screen is a bit too bright for me at the moment, called Rover. And so we're looking now at a magnification. We'll be looking next at the magnification of that part of the view. And there's 6 Comet, and there's Rover. Now, even on the screen at the moment, with a bit of I've got a bit of light coming into the room, I can see around here a few fuzzy patches, and this is Stellarium's attempt to show us what the sky looks like. But I'm afraid if you expect to see those looking like that just in binoculars, you will be disappointed. They're nothing like as bright as it appears there. So the way to find these objects is to start with 6 and draw a line between there and Rho, which is the double star, and go roughly midway between. and you can see a little triangle of about 9th magnitude stars. And that's when you know that you've got to right sort of part of the sky. And go back a little way there, and you can see M84, M86, and a few other galaxies in a line there. And if you then go back to this triangle and move this way, there's a star of about 9th, 10th magnitude, and just below that is the bright galaxy, what we call a bright galaxy, M87, one of the largest galaxies we know in the nearby universe, a really massive galaxy right at the heart of the Virgo cluster of galaxies. And visually, this is not very exciting. It's just like a lot of those other galaxies, it's just a fuzzball. And a few weeks ago, I did try and take a photograph of it with my 80mm refractor and CCD camera. And this is what I got. You can see, yes, it is just a blur of light. It doesn't look much better even in a big telescope. It's just a slightly brighter blur. And I was pleased to find that when I enlarge this image of M87 there, you can see there's a little spur coming out of it, the jet. And I didn't realize that it was possible to photograph that jet, which is actually coming from the quasar at the center of the galaxy M87. I didn't realize it was possible to photograph that with really quite a small telescope in my back garden near High Wycombe, not a very good sky at all. And so I was quite pleased to be able to do that. And I thought at first I hadn't got it because it was actually at the wrong orientation. If you look at the Hubble Space Telescope pictures of it, they seem to be at the jet seems to be at about 5 o'clock. But on the one I took the other day, it was about, what, 2:30. And I thought, well, it must be just a chance alignment of stars behind. But no, I checked. And if you look at a photograph which shows all the other stars as well, that is where it is. So I did detect that. I was quite pleased with that. Now, if you go back to this this map of the sky, look at this quadrilateral here, Corvus. Not very bright stars at all, but because they are by themselves and a nice compact group, they're quite easy to see, quite low down in the sky. If you're living up in Scotland and it's a misty night, you probably won't see them at all. But under reasonably good conditions, they stand out quite well. And there are a couple of objects in that area that it's worth looking at. Now, I must admit that when I photograph these objects, I use my go-to telescope, but we're going to look first of all at M104, Sombrero galaxy, which is, well, roughly speaking, take a diagonal, it's just off that diagonal. But I think just by casting around with a small telescope, you might have a bit of trouble finding it. You'd actually need to do a bit of real life star hopping to find that. And I took a photograph of that, and that's what I got. Not a brilliant photograph, but it shows, you can see that it's an edge-on spiral galaxy with a dust lane in between in the center of the plane of the galaxy there, and quite a bright nucleus. And that's worth looking for and seeing if you can observe it with a small telescope. You really should be able to. And we've had some very clear nights recently, also very cold nights. And if we get a few more, looking outside now, it's hopeful for tonight. So you might be able to find that. Also going back to Corvus, taking a line down like on the left-hand side of the quadrilateral there and moving down a bit, you come to a very low globular cluster in our sky, M68. And it's always nice to observe things that not everybody else does, and indeed photograph them. And I rather like trying to find objects that nobody else does and they're not so popular. There's a good reason why they're not so exciting, because globular clusters and M68, nothing very spectacular. But it's a bit different from all the usual objects in the sky. And this is the photograph I got. Nothing to get excited about, nothing like as bright as the globular cluster in Hercules M13, or indeed some of the others. But the fact is, it's really quite low in the sky. And I was very pleased to be able to get that in just a few minutes exposure. It showed up straight away on the CCD camera screen, so I was pleased to get it. So the message is that for the time being, with no bright planets around, we're going to have to start looking for these faint objects. And my message is, yes, try and find some of the things that nobody else is going for. a month ago, we had an exciting event, a nova appearing in the sky, and there was nothing to get to use to put a moon filter on for to dim the view. It was really quite faint, and here it is. It is Nova Cassiopeia, and this was as it appeared on 19th of March. And there are. Let's start off. The way I find it is the main stars of Cassiopeia are over to the left there. I follow the right-hand arm of the W until I come to this 6 magnitude star, which is called 4 Cassiopeiae, and move down a bit. There's the cluster M52, and just below that there's this pattern of stars here, a little group of stars, and this one here is Nova Cassiopeiae, and you can see it's got it's relatively bright compared with the other stars, but it's still actually 8th magnitude. And when it was discovered on the 19th of March, it was magnitude 7.8. So I looked again, and this is a photograph I took the other night, and there's 4 Cassiopeia again, and here are the same parts of the sky, and there is Nova Cass again, and you can see actually, if anything, it's slightly brighter. It hasn't changed over a month in its brightness, and this is really quite unusual for a nova. Here's a view shown by the a graph shown by the plotted by the American Association of Variable Star Observers, and the green observations are the visual ones, and you can see it started to just drop off a bit, and if anything, over the last few days, it started to increase again, which is very unusual. There are such things as most novae, I should say, brighten up, but then a week or two later, they're way down. So you would normally expect this to have declined to about 10th magnitude by now. But it's one of a rare class of novae that stay at the same sort of brightness. So it's rather nice to get an unusual object and not the run of the mill. So do take a look at Nova Cass. I don't suppose it's going to get any brighter, but it's certainly well worth keeping an eye on it. Unfortunately, it is circumpolar, so that we can find it comparatively easily. So that's something to look for. Now, I said that there are no planets, and you're going to have to wait until, well, the date down at the bottom of the screen there on Stellarium is the 17th of July, and I simply chose the 17th because it was when the moon was out of the way, and you could see the other objects in the sky. You can see Sagittarius down there, Altair, and the 3 stars on either side, 2 stars on either side of Altair, and they do point down to Saturn. No missing that. And there's Jupiter. You remember that last year the two were much closer together, and Jupiter was this side of Saturn, to the right of Saturn. Now it's moved on, it's closer to the sun, so it's moving faster in its orbit. So they will be returning, but you'll have to wait until certainly the July, until they are up before midnight. So at that time, that's when we can start returning to viewing the planets, and that's just before our next meeting in July, which is on the 30th of July. So that's how I am mentioning these things now. Normally we have meteor showers to talk about, but again, the autumn skies are not, sorry, the summer skies are not very good for meteors. We have to wait till autumn for the really powerful meteor showers, certainly start kicking off with the Perseids in August, and then going through the big things like the Orionids and the Geminids and the Leonids and so on. But the meteors do start at this back in July, and this is what we've got. We've got the Delta Aquarids starting on the 12th of July. Their peak is just about the same time as our next meeting on the 29th, 30th. So, but the ZHR, that is the number under ideal conditions, is only 5 meteors an hour. Nothing to get too excited about, and this is the source of the Delta Aquarids around that area there. And we also have the Alpha Capricornids also coming from a similar part of the sky. So if you want to find out where the radiant is, the Saturn is a good guide to them. Anything that's coming from the direction of Saturn, if it's coming from the left of Saturn, then it would probably be a Delta Aquarid, and if it's coming from the right of Saturn, it will be an Alpha Capricornid. So that's at the end of the period that we're talking about. So there we are. That's what's coming up in the sky over the next few months. Nothing exciting in terms of planets, I'm afraid, until we get to Jupiter and Saturn. But there's plenty to see. You'll just have to get out those binoculars, telescopes, and start searching for deep sky objects. And who knows, the sun might have some more activity. There are rumours of a possible aurora on the 25th. That's tomorrow. So if you're up in the north of the country, keep an eye open for that. It may even be visible farther south if indeed it does occur. So there we go. Now I hand back to Andrew, who will introduce our next guest, who's down, beaming faces down there already.
Excellent. Thank you very much, Robin, for that excellent overview of the night sky in the next few months. And yes, I must admit, I keep looking at Mars at the moment and thinking, gosh, there's all that stuff going on there at the moment, and just seeing it in the night sky in the evening, and our lovely evenings at the moment, it's great to be able to do that. So, but thank you very much. That's excellent. Okay, so on to Martin. So Martin Ratcliffe. Ratcliffe has was a secretary of the SPA some time ago, but and I believe started off at UCL actually, which of course is a great place to start. There we go. and is now in Kansas, and he's going to tell us about some of his activities with the observatories there. So thank you.
Thank you very much, and it is hopefully everybody can hear me okay, and it is a great pleasure to join. Yes. Thanks, Robin. Great pleasure to join the SPA again. When I was thinking of doing this talk, I kept thinking of meeting in the library off Holborn Road, which is where we used to meet back in the 1980s, which Robin will remember very well. So I'm going to get right onto this because, like I'm sure many people who've done talks before, and I'm setting up sharing my screen, which takes a minute on this computer. I have a lot of things to go through, and I probably have more things than I can really get through in an hour. So we're just going to, or in 45 minutes. So we'll just get cracking on it. And the story is going to be about my adventures in planetary imaging. And I just kind of by way of brief introduction, I've been contributing editor of Astronomy magazine for 25 years. I've been writing their night sky column, what's up in the sky, what to view with the planets for all that time. Of course, prior to that, I did a little stint on Astronomy Now. And then prior to that, wasn't writing anything really. So, and as Andrew mentioned, I did my astronomy degree at UCL. And since then, I've been working in the planetarium field. I worked at the Armagh Planetarium in Northern Ireland for 6-7 years, and then moved to Pittsburgh in Pennsylvania and Wichita, Kansas, which is where I am now. And that's why I'm somewhat heavily afflicted by a mid-Atlantic accent lilt in my voice. Whenever our family used to move around to different places in England, I was the first one in the family to pick up the local accent. And so I picked up an American accent quite early. And so all my American friends think I'm still English, and all my English friends say I sound American. So that's where the mid-Atlantic part comes from. I now work for a planetarium company called Evans and Sutherland. I've actually been working for them for a whole 3 weeks. I had the last year off due to COVID when the other company I worked for shut down. So it's been an interesting year, and I spent a lot of that year focused on planetary imaging. But this is my path for the talk. I'm going to begin at the White House, which you'll see in a minute. Then we'll come to Kansas. Then we'll go to Cape Town in South Africa, Bloemfontein and the Boyden Observatory. And then I'll talk about my planetary imaging from last year. So I did mention the White House. This is a little funny interlude, really. It's nothing to do with my talk, but it's an interesting topic, I think, for people to see. NASA held a star party at the White House in 2009 when President Obama was president. And so I had some great opportunities, surprising opportunities, actually, to be one of the planetarium people presenting two kids in the dome. You'll see the dome on the left. It's an inflatable dome. And the two people with me came around and wanted to see how to get in and out and what we were doing. And you'll notice the gentleman on the right of me, or on my left, but on the right in the picture, is actually leading President Obama in the lower right picture with his little daughter Sasha, and Malia is over here. And so he brought them into the dome, much to my surprise. I was giving a planetarium talk to 25 school children, and I heard this commotion behind me, and there is President Obama on his hands and knees crawling into the inflatable dome. And what do you say? Well, you say, well, hello, Mr. President. And it was a remarkable and marvelous experience. Probably, I realized then why I had been training myself in planetariums was really for that moment. And you never know when you're working what's going to happen, and suddenly you're put on a stage where you really have to perform very well. And at that moment, you're glad that you did all of your training. So that's an aside. I wanted to show you where Kansas is. Robin, in his email to you all, said I'm in far-flung Kansas. So this is how far-flung I am from you at the moment. Here are the Great Lakes in the upper right. Kansas is this square piece of land in here. It's about the same area as the UK and has about 3 million people in it. So let that sink in. Most of the state is farmland. Wichita, Kansas is about here. Oklahoma is down here. Denver is over to the left here. This is Texas. And this is an area of the country that has a semi-arid climate. We usually get about 280 clear days of the year, which is not bad for around here. But April and September can be stormy. And the reason it's stormy is that we get, and this picture will show you, we have warm air coming up from the Gulf that flows north. We have cold air from Canada flowing south, and they collide over Kansas and Nebraska and Oklahoma. And where that air collision is can get quite violent. We can get tornadoes, although I've been here a long time now, 20 years, and I've never seen a tornado yet, although they've been close. So they put a bit of clarity to the mind when you're thinking about what tomorrow might bring. So anyway, this is a nice picture showing what can happen in Kansas. This was last summer when I was out in the morning trying to observe Comet Neowise, and Wichita is right underneath this dark cloud. This is a thunderstorm that suddenly popped up. We had clear skies in the morning, and then all of a sudden this storm came in and blotted out the sky. Anyway, so that's where Kansas is. Kansas City is up here, for those who need some more geography. That's where my daughter is a dentist. And anyway, we're now going to fly over to South Africa. And because of my job in the planetarium world, I traveled to different planetariums, training staff, learning how to use our planetarium systems whenever we installed a new planetarium. So I just want to orient you to where we are. Here is Johannesburg, and southwest of Johannesburg is Bloemfontein, which is where we're going to go. Far down here is Cape Town. We're going to visit there briefly first. Cape Town is an absolutely beautiful area of the world. If I could move there, I would. There are a few other places along here that I have visited. Durban in particular is a very nice city on the coast. But it turns out Bloemfontein is a semi-arid climate, 35 degrees south of the equator, and Wichita, Kansas is semi-arid, 35 degrees north of the equator. And so where I live now had a lot of similarities to Bloemfontein, and when I got there, I really felt at home. Some of you may notice a town here called Kimberley. That is fairly famous for some nice pieces of compressed carbon they pull up from the ground called diamonds. That's where the diamonds come from. So that's your orientation. I wanted to mention Cape Town. I've been there. I'd never visited Cape Town until I was older than 50 years old. And then I visited there now probably a half a dozen times. It's a wonderful area, rich astronomical heritage, in part because of this site here. This plinth here marks the location where Sir John Herschel set up his telescope between 1830 and 1833 to observe the southern sky. And you see the Table Mountain in the background, and look in particular at this shape of this rocky outcrop. Here's the field. His location is now a school, and it's usually gated. I got access to take this photograph. And here's the playing fields down at the bottom. You can see a football goalpost there. So here is the more detailed picture, and I want you to remember the outline of this, because there's a very famous picture of this outline drawn by John Herschel. Here it is. And this is the same mountain outline with the location of his really wonderful 20-foot equatorial telescope from where he viewed the southern skies. So really, as I say, historical place to go. There's also a Royal Observatory there. Here's that rocky outcrop of Cape Town again. Here's the really beautiful library in the observatory. Here are the front doors. This is a photographic lens that was used in the 1890s for the Cape Durkmusterung photographic star atlas, which was really, they have a very rich set of astronomical equipment, and you're going to see more of that in this talk. Bloemfontein. So we're going to fly to Bloemfontein, and here is an aerial photo that I took. There's a giant water tower here. This is a large hill. It's actually a nature reserve, and in the middle of the nature reserve is a dome, and this dome used to be the Lamont Hussey telescope with a 27-inch refractor in it. It was run by the University of Michigan. And this is a photograph I also took showing you that it really is a nature reserve. This is a beautiful giraffe. They have two of them that rove around. When you drive up to the observatory, you sometimes see them walking around, grazing. Little bit of history to the Lamont Hussey Observatory. It had a 27-inch Clark refractor, a really beautiful telescope. As I say, this was built by the University of Michigan and operated for many years. It closed down in the middle part of last century. And after a while, the dome was sealed, wasn't being used, but the university took on a project to build a planetarium inside the dome, and I'll show you inside in a moment. But some years after that, they found the pieces of the 27-inch telescope. It was actually sitting in a fire station in town. Here is where they found the pieces in the fire station. I wasn't kidding. Just rusting telescope tubes. And it's now been resurrected in front of the old dome as an iconic piece of historical telescope equipment. The lens is in the University of Michigan under safekeeping, and it will probably never be used in this telescope again. But there's the telescope. Here inside is the planetarium, and they've retained a lot of the appearance of the old dome. You can see the dome wheels here and the brick walls, but the planetarium was built inside, and I spent a long time in this theater with the staff and was there for the opening. I gave the opening show to many dignitaries who sat in these seats. It was a really beautiful location and a beautiful place. Here's an aerial shot of the dome today with the telescope 27-inch outside. And here's the planetarium team with an artist and a couple of scientists. She's a geologist. He's a professor of physics. Magdalena Schock here actually ran the first Spitz planetarium projection system in Cape Town many, many years ago. And so she has a long teaching background. So all of these people are now close friends of mine. You tend to build these relationships when you travel around the world, and it's certainly one of the most gratifying and pleasant places I've ever had the pleasure to visit. Bloemfontein has a bit of older history, which is much more sobering. It has this National Women's Memorial for all the women and children who died in prison camps during the Anglo-Boer War at the end of the 19th century. And they have this incredibly moving display of names on here. Now, Bloemfontein, just outside Bloemfontein, is home to Boyden Observatory. And Boyden Observatory has a very long history. It began its life in Arequipa, Peru, as part of the Harvard Observatory Southern Hemisphere Station, and it was moved to Bloemfontein in 1929 by Harlow Shapley, who was the director of Harvard at the time. Harlow Shapley actually had some of these trees planted. They're now much taller than when he was there. This is the library. Here is a telescope we're going to be spending a lot of time with. It has a 13-inch clock refractor inside there. Here's a 60-inch telescope. It used to have a 60-inch mirror that was built by Ainsley Common in England, and it was moved, eventually moved into the library because it was not perfect in optical quality for what they needed for modern astrophysics. This telescope here, I think it's this one or this one, is used to house the Almar Dunsink Harvard telescope. This was a remotely operated telescope by Almar Observatory and Dunsink Observatory in Ireland. And me being in Almar, I heard about this telescope a lot, but had never visited Boyden. But I heard a lot about Boyden. Boyden kept coming up in readings that I was doing. And so obviously it was proving to be a big attraction for me personally. And not only that, but on my first visit to the United States in 1979 as a 20-year-old boy, I visited Lowell Observatory and I bought this book called Lowell and Mars, A Famous History of Observing Mars. And I read this in the 1980s. And in here it says there are several new observatories, the most notable, the Harvard College Observatory's Boyden Station, high in the Andes in Arequipa, Peru. So this was built in the Southern Hemisphere for observing the 1892 opposition of Mars, because that was one of the closest oppositions of Mars. So there was a seed planted in my head. Little did I know that some years later, won't say how many, actually it was about 40 years later, that would come to, I would get a strong echo from that book. The Boyden Observatory's 13-inch Clark refractor has a really interesting history. The Harvard director at the time, William Pickering, had Alvin Clark build the telescope, and they loaded it up and put it on Mount Wilson in 1889. And Pickering said, "I consider this the point of all others to place the largest and finest telescope in the world." By the spring of 1889, Harvard had installed a 13-inch on the mountaintop in this building. But soon after, this didn't work out very well, and they took it down and they moved it to the Southern Hemisphere in Arequipa, Peru. Here's a view of the Harvard station in Arequipa. Here's the 13-inch installed as a close-up photograph from the Harvard College Observatory website. So that was in the 1890s, and then it got moved to Boyden in Bloemfontein. So now here's my little story. A year before the perihelic opposition of Mars in 2018, I was writing my column for Astronomy magazine and realized that this very, very close opposition of Mars in 2018 was a unique one for me. It's a unique one for everyone because this year or last year, the opposition was a little bit further away, still very good. The next 8 to 10 years after that, And by the way, I should note that around about this time, 2025 to 2027, I'll probably retire. And so 2033 to 2035 is the next time there'll be a perihelic opposition, and I'll probably be sitting in my comfy chair in front of a crackling fire reading books and not traveling to the southern hemisphere. So I realized this was probably my final opportunity to see a perihelic opposition of Mars from the southern hemisphere. And I pondered to myself, who do I know in the southern hemisphere? And of course, Boyden, Bloemfontein, Boyden Observatory, I knew the staff there. I trained them in the planetarium. So I instantly sent off an email to my good colleague and friend, Professor Marty Hoffman, and said, could I come down and observe Mars with the 13-inch? And within an hour, he had responded and said, yes, of course. So I then realized that this was a long-standing wish of mine, dream of mine to do this. And so I started to make it happen. As it turned out, I was visiting Europe in July 2018 for some work. And so then I could fly from London to Johannesburg and then on to Bloemfontein relatively easily. And then I had some more work to do back in Europe the week after. So I spent a week in July with this telescope. And by the way, Mars goes overhead, which if you're used to observing from England or here in North America, it's not often that Mars goes overhead. So it's very thrilling. But there's more. There's a lot more history to cover with this telescope and Mars, which I found quite amazing. By the way, they do have the common 60-inch mirror here. Ainsley Common also made a famous 36-inch mirror, which he sold to Crossley, and he donated it to the Lick Observatory. So there's two very famous English mirror-making telescopes in South Africa and one in the US. But here's the most remarkable thing about also the history of Mars and Bloemfontein. The Lamont Hussey Observatory I already mentioned, the 27-inch, turned out Earl Slipher took the very first color photo of Mars with that telescope from Bloemfontein. And here is the camera. The camera was found in an old wooden box. This is the original box here, in the corner of an office somewhere, and it had this brass tube in it. And it was really quite remarkable. And they realized that this brass tube was Earl Slipher's camera. You can see it in the lower part of this display here with Slipher on the right. And here's the detail of that picture. And you'll notice the little number 2 on there. And that number, there's also a number 1 camera, which is the one that's on display. So the very first color photo of Mars was taken with that 27-inch telescope. And here are images from that telescope taken in 1954 by Earl Slipher. These are on loan to the university in Bloemfontein, the physics department. These are Harvard College Observatory glass plates showing images of Mars and how they were developed. But not only that, here is the very first black and white image taken of Mars in 1888 with the 13-inch. And this was on June 16th, 1888. And they also had those on loan while I was there. So these little dots here are negative images of Mars taken in 1888 with the same telescope I was spending a week with. So I had, if you're an observer for Mars, you're probably having hair standing up on the back of your neck by now. I hope so, because that's how it made me feel, was tremendously excited. Earl Slipher produced that famous book here called Mars, a photographic story of his imaging of Mars in the 1950s. And these are photographs through a blue filter comparing the images from Flagstaff, the famous 24-inch telescope at Lowell Observatory, and the ones made in South Africa at Bloemfontein with the 27-inch. So there's a whole book about this South African connection of Mars. So what about Mars in 2018? Well, here I am observing Mars, and you can see how, by the inclination of the telescope, how high Mars is. It's actually quite difficult to reach it at that point. Here it is in the earlier evening, a photograph I took with a 13-inch, the famous telescope that took the first black and white pictures of Mars, looking at Mars in 2018. And it's a dream telescope to use. Turned out 2018 was the first time anyone had attached a modern video camera to the back end of this telescope. I have a filter wheel here and a computer running it. The old mechanism for focusing was tremendously difficult to turn. The folks at the university came and oiled it up and made it a little easier to use. And so I spent many nights down on my hands and knees photographing the telescope. At one point, I looked above the telescope after viewing Mars through the eyepiece, and I saw Mars above the orange tube, and I had to take this photograph. Well, it's not a handheld photograph. I put my tripod there to get a really nice, clear photo of Mars, and what it was actually like sitting at the eye end of this giant telescope looking at the red planet. So a very evocative photograph, some great memories for me there. Here's the Milky Way. You see how clear it is. There is some light from Bloemfontein, about 20 miles away. And here I am actually viewing Mars right overhead. This is a longer exposure photograph of the Milky Way I took. This is looking straight up. It's rather, I consider this a rather garish processing now. I wouldn't do that today, but that's how it turned out in when I processed that a couple of years ago. Another link to kind of my earlier history of astronomy was the ARMAR link with the Armada-Sync Observatory. This fellow in the middle is Eric Lindsay. He was the director of the ARMAR Observatory. He visited the United States a lot. He knew Harlow Shapley personally. He was seeing all of these planetariums being built in the 50s and 60s in the United States and decided he wanted to build a planetarium in Northern Ireland next to his observatory. And of course, that became the ARMAR Planetarium. First director was, of course, Patrick Moore. And it's a place that I began my career in planetariums as well. Oh, and this is Earl Slipher on the right-hand side of the photograph, the gentleman who took the first images of Mars from the Southern Hemisphere with his color camera. So here is, of course, I get to observe Mars in July 2018, and those of you who recall, timing was a little bit bad because Mars had a global dust storm during July. So that was a bit disappointing and challenging. This was incredibly difficult here to pull out even this detail. There's the North Polar hood. You can maybe see some vague markings here. This shows a computer-generated map of what should be visible, but wasn't really visible. But I can tell you Jupiter and Saturn were absolutely stunning. They also passed overhead, and I got many images of those as well. But here's just a comparison of 2018 to 1888 with the same telescope. That's the point of this, is to show that comparison. One thing happened when I got home after that trip. I got out my own 14-inch telescope and imaged Mars. It was a beautiful evening. The Martian atmosphere had cleared a bit. Here's Solus Lacus, and Valles Marineris is in here as well. And I sent this off to Richard McKim of the BAA, Mars section director, and he said, you have a dust storm firing up in this valley right here, this yellow spot. So that was exciting. This is what I considered in 2018 a very good picture of Mars. It was nothing like some of the expert planetary images, but I was very pleased with that image. In 2018, I also got to visit Lowell Observatory in Flagstaff, so doing the full Mars circle, if you like, of connecting these telescopes together, the 27-inch in Bloemfontein, the 13-inch in Boyden, and then this 24-inch. And I captured a few images. I had about 10 minutes on the telescope between twilight and when the public came in to capture an image. My filter wheel failed, but at least I got a nice infrared capture through this grand old telescope. Okay, so now I'm going to talk about imaging Mars. This is the main part of my talk. And so I image Mars through color filters using a fast, high-rate video capture camera. This is the resulting color image showing Syrtis Major. This again was 2018. So I imaged through a red filter, a green filter, a blue filter, and an infrared filter. You notice the infrared gives the most clarity through the Martian atmosphere because it can essentially see through any dustiness. The blue is really showing up any clouds in the atmosphere, and it shows off the South Polar Cap quite vividly. This is my setup. It's a Celestron C14 Edge HD. You can see my wire cable management is not a picture book quality, but it works. I have a guide scope on the back. Here is the filter wheel. I have an ASI 290 monochrome camera, a Barlow lens, which I'm going to talk about in a minute, and then a focuser. And the focuser is temperature controlled. Here's the temperature sensor. So that can help with focus. So imaging Mars is tremendously challenging. And so I gave myself the challenge in 2020 to really improve everything that I could and to really pay attention to all the detail, because I couldn't understand why I, with a 14-inch telescope, was not getting the same kind of quality images as some friends I have in other countries. One in particular, Clyde Foster in South Africa, has been a great help to me in understanding some of these fine details. So our challenge is that we sit underneath a very dynamic pool of air that never sits still. What we hope for is a laminar flow with no turbulence, and none of us gets that really unless we move to locations where observatories have already been built or picked, or you get to fly to Barbados and observe from Barbados. One of the fascinating articles I found in my historical collection of Sky and Telescope magazines was here in September 1971. There was an article on seeing and scintillation. It followed an article about telescopic observations of Mars in 1971 by Gerard de Vaucouleurs, a very famous Mars observer. And here's the article, part of it. A fellow from the Jet Propulsion Lab was looking at what happens when you have either a small telescope or a large telescope. And the initial wavefront from the planet, the light that's coming from the planet, goes through our turbulent atmosphere, and we get this distorted wavefront. And so it makes the images wobble, shimmer. And we're all very used to this, looking at planets through telescopes. But it turns out if you use a small telescope, you can sometimes just see an undulating pattern on the planet, whereas with a large telescope, this wavefront is completely distorted and it's not coherent anymore. So you end up with pictures like this. This is an example from the article showing the resolution of the solar atmosphere, the granulation, and you see very fuzzy areas of it, and then other areas are clear. And the article said, if we could build a system that could capture frames very quickly and capture these still pieces, we could reconstruct an image that is really attaining the resolution of your large telescopes. That's in 1971. I just find it remarkably prescient that he was able to write that, because nowadays we can all do that. And not only that, the cameras are under, I don't know, 200, 300 pounds maybe, and the software is free. So it's a remarkable age we live in that we can really do this. His article also mentioned this piece here at Boyden Observatory, a hilltop near Bloemfontein, the seeing is good until the inversion rises to the height of the telescope, and then it deteriorates greatly due to turbulent mixing. So here they're using Boyden as the example of where you can get good seeing and then also bad seeing. One of the things that I use for determining whether the seeing is going to be any good one evening is called Meteor Blue. You can see the reference at the bottom there if you want to go and check it out, and you can input your own location. This I found to be fairly good guide, but not a perfect guide. Here it's indicating the seeing conditions are a 5 out of 5, but here the jet stream is moving at a very high velocity. So when this turns red, it's not going to be a very good night. So what I decided to do, in Kansas, daytime temperatures can easily reach 32 degrees centigrade. That's about 92 Fahrenheit. And in the observatory, it reaches over 40 degrees centigrade. That's over 100. And so 40 degrees C is quite warm. Otherwise known as bloomin' hot, to not put too fine a point on it. And for a long time, I hadn't bothered trying to cool down the observatory. I thought I could just pull back the roof and wait an hour or two. Well, it turns out a Celestron telescope of 14-inch size can take 2 or 3 hours to cool down, and that's too long. So I put in an air conditioner. My wife helped me put in this air conditioning unit, and I can get the telescope down to, once the sun sets, I can get the telescope down to pretty much ambient air temperature within an hour of twilight, and then I can be observing right away. So here is a comparison of what you should see for an out-of-focus star with this telescope. These are actual video captures, and I do this to work on collimation. Not sure I can move that out of the way. I don't know whether it's in your way. Let me go back. Okay, just wanted that bar out of the way because it's my apologies. Okay, we'll just keep going. It's missing off my headline, collimation. So you want to see these perfectly symmetrical concentric rings for an out-of-focus star. And if the temperature is pretty good in the tube, you may only see a little bit of heat affecting the image. Here is an image that has been completely affected by turbulence, both in the atmosphere and in the telescope, and it's just destroying the star image. This is what you really want to see in an in-focus star is, and this is sometimes about the best I can get. And once I started using the air conditioning unit, I started seeing the airy disks on stars that I'd never seen through that telescope before in Kansas. It was remarkable. Just the addition of that cooling system completely changed the quality of images that I could achieve. So that was a major component. And the other major component was getting the collimation right. So what I would do on evenings is, and I've learned this from Damien Peach, whose videos are very good on explaining the importance of collimation. And I have the collimation screws, and I watch a video image of an out-of-focus star, and I capture frames and measure to see how much I need to move. And I've sort of calibrated that in my own mind. And sometimes a 1/16th of a turn on my collimation screws is enough to center this dark spot right in the middle of the stellar image. And so I decided to spend a long time doing that. It's quite frustrating at times. I have to climb a ladder and do this. But as Damien said in one of his talks, you want to spend as much or more time focusing and collimating than you do capturing video, because if you're capturing video and you haven't collimated properly, you're really wasting the time and you won't get good image. So what you really want as well above you, above your head in the atmosphere, is coherent turbulence. And I'm going to show you the best way, instead of talking about that, is to show you some examples. So I'm going to skip out of my, I have this lined up and I'm hoping it all works perfectly first time. So I'm going to run a video and hopefully you can see it. This is an image of Jupiter, and you can see the red spot here. This is kind of incoherent turbulence. You can see the entire limb is wobbling horribly. There are pieces of the image dropping in and out of focus at different times. It's quite random. I can still get a good stack out of this video, but it's not great. My next one is even worse. Now the image is hopping all over the place, and you see that it's moving as well in the frame. And the reason it's moving is half a mile away I have train tracks, and when the train goes by, this image wobbles even more than you're seeing now. It's quite disturbing. I realize I have one of the most accurate seismometers on the planet, because even a train moving half a mile away really makes a big difference. But here's what I mean by coherent disturbances. Here you can see Jupiter's remaining pretty still. The image, you can see all of the features on the disk. None of them are really dropping out of focus. You're probably not seeing this very clearly over the internet line, but I can tell you from where I'm sitting, the red spot is on the left. A lot of features and plumes and festoons here that are quite clear. And that's a very rare night for me. So that's really one of the better nights. The problem is, of course, you don't know beforehand what you're going to get. So you have to go out many nights and hope that you capture something good. So here is a capture of lots of black and white frames through red and green and blue filters, and about 10 minutes apart, 5:14 a.m., 5:24, 5:32, 5:37, 5:42. And I put all these together to show you how different the atmosphere can be, because you can see these two on the left and the two on the right are quite good. They're actually some of my best images that I've ever managed to get of Jupiter during this period of cooling my telescope and what have you. But this image, 5:32 in the middle, is absolutely beautiful. And it just so happened that during those few minutes that I was recording, even though I was doing constant recording of Jupiter, this one, I was given the absolute perfect laminar flow over my observatory and got really a great image. So you never know. You've just got to record a lot and then process it and see what comes out good. At least for people who live in kind of normal climates like I do and you do in the UK. I wonder if, Robin, you could give me an idea of how long I have left.
Well, you've been going for about 3/4 of an hour now, I guess. So there's no caretaker to rattle keys.
Right.
You can carry on by all means. It's fascinating stuff.
Okay, good. Well, I'll do, well, let's see how we go. I'll do another five or so minutes. I'm going to skip through this fairly quickly because we're getting near the end anyway. I was going to spend a lot of time discussing fire capture and how we capture images. Here's an actual image capture of Jupiter. There are lots of settings here. The most important ones are, and I'll just show you on here, is gain, exposure time. And actually I have gamma on here, which I never do. So I don't know why I have that picture. So I always turn that off. The trick of capturing planetary images is getting a decent histogram, about 75 to 85% of intensity. And you can increase that by increasing the gain, but that increases the noise. But when you increase the gain, you can reduce the exposure time, and that increases your frames per second. And really what you want to do is get a very high frames per second, as high as you can. Here it's only 56. So it's a challenging game between balancing gain, not going too high, and reducing the exposure time so that you get a histogram that is a decent level and you get a high frame rate. And there are modern cameras now that can do this really well. Some cameras are better than others. Here also I have my filter wheel, and I can preset the focus position on my focuser. And one of the advantages I found once I'd done lots of practice was that I could focus very nicely on the infrared, and then I knew the offset for the other positions. And every 10 or 15 minutes I would, or 15 minutes to half an hour, I would check the focus position. I would find it would actually drift. So that's something else I spent a lot of time doing, making sure I was in focus. And then also what you can do is you can select a region of interest. So this camera here is 1900 by 1000 pixels, but I've selected 250 by 250. And you just select an area around the planet. You can just click and drag a square around Mars. That reduces the number of pixels you're saving, and that also increases your frame rate. So that's a very beneficial thing to do. But of course, your tracking has to be spot on to keep Mars in the middle of the frame. The other software we use is called AutoStackit, and this you import all of your video frames, you analyze it. One thing I learned is to set this Laplace setting high. I used to have it on 4. It turns out 6 is better. And the other thing I learned from my friend Clyde in South Africa, I tended to use very small alignment boxes here because I was looking for fine detail. That's the wrong way to go. If you use larger boxes, then the software can determine the coherent pieces of the image and stitch them back together. If your boxes are too small, all it sees is noise. So you want these to be a reasonably good size, and so that's a typical size I would use for Mars. Also in AutoStack, you can have this automatically open in Registax. Forgive me for not spending a lot of time introducing this software. There's lots of video, very good video tutorials on how to use this software. So I recommend you go and listen to those extensively because we have Jupiter and Saturn coming around in the next few months this summer where we can start imaging again. But I want to show you the power of Registax because they have this system called wavelets. And what wavelets does is it analyzes the number of pixels of certain sharpness at different, well, it's actually analyzing the image in a power spectrum. And it's looking for how many do we have fine detail, how many do we have large detail. And I'm not describing that very well, but I'll show you the effect of wavelets. So this is a stacked image of Mars. And when I put the wavelets on, this is what happens. So I'll go back and forwards a little bit. And what the wavelets do is essentially remove any turbulent structures that are random in all of the between the frames, and it retains the signal that is persistent in all of the frames. And it enables you to sharpen that up. So this is really illustrating the power of Registax in sharpening that image. And again, I hope you can see that over the internet, that it's coming over reasonably clear. I was going to spend a bit of time on cameras, but I'm actually going to skip over this part. Part of the reason was I was using this 178 camera for a while, and last year I decided to go for the 290, which a lot of planetary images were using for a very particular reason, was that it was more sensitive towards the red end of the spectrum. And this increased sensitivity also allows for a brighter image. And if you have a brighter image, you can do a higher frame rate. And higher frame rate is what you want. There's a new camera out that came out a few months after. It's an ASI 462, or QHY also have it for a 462. This has a remarkable infrared sensitivity. So for infrared, it acts, both RGB colors are essentially acts as a monochrome camera in the infrared and as a color camera in the red, green, and blue. So you have the best of both worlds, a mono and a color camera, all in the same camera. This has really become the standard camera to use. So again, this is my setup. I'm going to show you some images shortly, but one final point about the Barlow lens. I couldn't understand why my 2x Barlow was creating very faint images. And it turns out this is the reason. Follow this blue line. My 2x Barlow is only 2x when it's 0 millimeters from the camera. But of course, my camera was behind a filter wheel, so I was back here, and I'm actually at 3x. I was about an inch, or 2 inches further back. So a regular Barlow actually increases magnification the further back you go, and that makes your image dimmer and reduces your frame rate. So I then decided to plumb for the Power Mate, and I got the 2x Power Mate, which maintains the 2x magnification all the way across. It doesn't matter how far back your camera is. And that was also a very critical part of my system. So now on to images, and I'll just spend 5 minutes on this, and then we'll wrap up and do some questions if that's all right. This happened last year. Clyde Foster, my friend in South Africa, was imaging in the methane band and turned out to discover a bright spot next to the red spot. It wasn't there the night before. He noticed that. He sent it off to John Rogers at the BAA, who sent it off to the folks at NASA who were running the Juno mission. And it turned out 2 days later, the Juno spacecraft was going to do a close flyby, and their cameras could target this. And this became known as Clyde's spot last summer. It was all over the news. Here's the red spot, and here's Clyde's white spot that he discovered. So that ended up being existing for quite a long time. And then another thing happened in August when John Rogers also announced that a fellow in Japan had noticed a new white spot on Jupiter in the northern temperate belt, excuse me. And I noticed I'd been observing that same day, that same night, and his central meridian measurements were the same as mine. But I was 1 rotation of Jupiter earlier. So I ran back to my file and looked at all of my images. And it turned out that I did indeed have a pre-discovery image of that white spot. There it is. And that was, if you note the time, was at 3:48 UT. And there's another gentleman who you will know well, who was also using a bit of a larger telescope. This is Damien Peach at 3:47, 1 minute before me, and there he has the white spot. So he got the earliest pre-discovery image. I got one 1 minute later. That was very exciting to be involved in that collection of data as well. I'll skip over that. What I want to do is finish up showing you some images of Mars that I took during the summer in July and August. August, it was starting to get very nice. These are what I consider by far my best images up to that point. And Mars still had about 25% of size to go. I could track the Mars polar cap receding. That was picked up by fellow Ethan Scagell in Forbes magazine, who ran some of my pictures in his article. And also this familiar look now of color imaging of Mars. So what of the Mars opposition in October 2020? How good was it after all of my effort and practicing? You've got to practice early before opposition. And so I will leave you with a couple of pictures of which I was incredibly satisfied. So here was one in October 22nd. showing Sinus Goma here. That was a very nice image that I was pleased with. And then another set of images. This was from October 5th, which turned out incredibly well as well. Some detail I've never ever seen on Mars before, ever. And I could see them easily with my telescope. And there was this one, which is my final image showing Sinus Syrtis Major. And down here is where the Perseverance rover has landed. So that's my final image. And as you can see, it became quite a success. It was a lot of work during June, July, and August to get ready for the opposition and make sure I was getting decent images. I'll leave that up. There's some more image guides. People can look at those, and I'll stop there. Thank you. Thank you very much for listening.
Thank you very much, Martin, for a lovely talk and some amazing images and wonderful anecdotes. So a couple of things from the chat. So Wendy said, really lovely story about Barak, and Colin Pryor. Oh no, sorry. The question from YouTube, AstroKev, was interested in your White House anecdote. Did President Obama stay for the rest of your show, or was it just a fleeting visit?
It was a fairly fleeting visit, but he stayed in probably 5 to 7 minutes. Malia sat right next to me. Sasha cuddled up on her dad's legs, very shy. And they asked questions about why we have seasons on the Earth. And so I had to very quickly put together a little presentation of showing the tilt of the Earth and going around the sun. It turned out normally presidents, when they have events on the south lawn of the White House, they stay maybe 20 minutes and then go back into the house. And he stayed outside an hour and a half for the astronomy session.
Excellent.
Really enjoyed it.
Yeah, that's excellent stuff. And I really loved your image with Mars almost overhead and the telescope underneath. I thought that's really amazing. So I wonder if there are any other questions from people.
I don't see any others in the chat.
Any others? Anybody want to raise a hand, or that can't see anything else, but thank you very much again, Martin. I'm wide-ranging and love the just 1 minute difference to for the Jupiter image, and
that was a funny one, actually. A bit of the detail of that story was I got so excited that I'd got a pre-discovery image of that and labeled it up, and I was putting on the central meridian, and I sent them off to John Rogers, and it came back a few hours later saying, I think you have this mislabeled, Martin. What I'd done was copy the wrong time onto the wrong images. So for a moment, a few hours, it looked like I had the earlier image than Damien, but once I corrected that error, mine was a minute later.
So very close, though.
Yeah.
Fantastic. And thank you very much. And some of the Mars imagery and just the going around the various different observatories. Wonderful talk. So really thank you very much. Much appreciated.
Thank you.
So and all the way from Kansas as well. So okay,
it's easy now, isn't it?
Yeah. So that's great. So the next SPA meeting, of course, is in July, so 30th of July. So Robin, anything to add?
Nothing from me, thanks very much. I just really enjoyed Martin's talk, and it's always nice to see a bit of actuality and a bit of background and hear people's travel stories, particularly when they're very astronomically related as those were. And I'm sure Martin's got many more stories, and we'll try and plunder his treasure chest of stories in future meetings. So thanks very much, Martin.
Thanks very much indeed.
Yes. And then hi, Dave. Nice to see you as well. Thank you very much.
bits of telescope in a fire station. Yes, just amazing, amazing range of stuff. So thank you very much, much appreciated. Yeah. So the next meeting, 30th of July, and we have George Seabrook to talk about Gaia and mapping the Milky Way. So so that should be fascinating. So thank you very much, everybody, for attending this afternoon, and go out and enjoy the rest of the day. Okay. Thanks a lot. Yeah.
Bye.
Bye.